Welcome back to the video lecture series for Introduction to Data Programming using Scala. In this video we continue implementing our binary search tree based map, and in the last video we finished up the get method. Now note, I say we finished this up, we technically haven't tested it. For one thing, it's actually kind of hard to test get until we've written the add method. So at this point we can't add anything to our tree, which means we can't really build the tree. So we need to do that. After we have that, it would actually be good to test both the get and the add and make sure that they work the way that they're supposed to. So this adding method, what does it need to do? Well, first off, there is a special case. If the root is equal to null, then I'm going to do one thing, else I'm going to do a bunch of other stuff. Two equal signs. If it's equal to null, I have nothing there, so I need to set the root equal to a new node that has the key and value that were passed in. This is passed in as a tuple, so kv._1, kv._2, and it has no children. Okay, so that's our simple special case for we've just added the first node into here. So what should happen after that? Well, if we look at our tree, if I were going to add, say, a 1 to this, I notice that the 1 is less than the 5, the 1 is less than 3, the 1 is less than a 2, 2's left is null, so I would stick it right there. And in general, the approach is we should descend through the tree in our standard approach, compare and either go to the left or the right, until we get to a situation where it's supposed to be null, and once we hit that, then we should place it there. Okay, so that's going to be the approach that we want to take. So how do we do this? You know, actually, I've started writing this way. There's a really nice way to write this that goes recursively instead. Let's do that. Let's put a recursive function inside of here. And this recursive function is going to take the node that we are checking, and we're going to make it so it returns a node. And in some ways, that's what makes this easy. In that the root will automatically be handled in the way that we're doing this. Note, this version is going to be simpler to code. It's not quite as efficient. It's going to do some extra assignments that we don't need. So the way I had started writing this might actually be better in certain situations. Okay, so what is supposed to happen here? Well, we might actually want to look at the API, because there is one situation. What is the plus equals supposed to do in the case of the key is already there? If the map already contains a mapping for the key, it will be overwritten by the new value, because that is a possibility. We basically have three possible situations for the key, kv._1. You know, I really hate typing in some things like kv._1. So I'm going to do key value value equals kv, just to pull those out, and that way I can use them inside of my recursive function. So what are the possibilities? Val c equals comp of the key that I'm adding to in's key. Now at this point I automatically go, whoa, I did something dot key, and I don't have a check to make sure that something isn't null. So I need to have my base case for my recursion here. If n is equal to null, then I'm going to return a new node that takes key value null null, which was basically what we had written previously for that special case for the root, except it's not actually a special case for the root. I want to do exactly that for any time that I get down to a null, whether it's the root or whether I've walked off the end of the tree. After I've done this comparison, what are my possibilities? If c is 0, then what's supposed to happen is we are going to overwrite the value in the current node to be the new value. And I need some curly braces here because this then returns that node. Else, well, we still have two possibilities. If c is less than 0, then that means that we need to go to the left. So I'm going to call recur. So first of all, n dot left equals recur on n dot left, return n. Else, if it's not equal and it's not less, it has to be greater than. So n dot right equals recur of n dot right, and return the same node. I immediately notice all three of these options return this same node. The only option that doesn't return it is up there. So I am going to delete all of those and just say when we get to the bottom here, I'm going to return n. Okay. And I could tighten this code up a bit, but this is probably sufficient formatting. So the way that the add works is I pull out the key and value just because I want better variable names for these, because I don't want to type kv._1 and ._2. I find those challenging to read and not informative to most people when they look at them. And then I have this recursive function, and all this does is it says root equal to the call to the recursive function. Anytime we hit null, we return a new node. If we don't hit null, then we do the comparison and check equal, less than, greater than. Now, why do I like this recursive version as opposed to the non-recursive version? It turns out that in the non-recursive version, so it's really, the magic is in this and in the root equals. When you write the non-recursive version, when I create a new node, after I've created it, you have to decide whether that was the left of the last thing that we hit or the right of the last thing that we hit. Basically, writing it the other way, I can't walk off the end of the tree. This approach, because of the way the recursion works and because the stack remembers the operations, literally walks off the bottom of the tree. So when I'm adding a 1, it goes less than 5, less than 3, less than 2. Oh, hey, I fell to null. If you do that with an approach that uses a while loop, if you've lost yourself down here at null, you don't know what to link onto, and that's a problem. Technically, I don't know what to link onto, but the call stack does. And the call stack is remembering, hey, you were in this node, and it remembers you went to the left, so whatever you give me back, I'm going to assign that pointer. And that can simplify your code significantly and make it easier to work with. So that's the add method. Now that we have the add method, maybe we should consider writing a test of this. Let's do it. New Scala class, test BST map. Let's pull open one of our other tests, largely just so that we can pull in the imports. And what do I want to do? Well, following what we've done before, var map equals, is a BST map. Oh, what do I want this to map? How about, I'll keep it simple for now. Equals null at before make map equals new BST map. Sorry, missing a def. Oh, actually, I might not even need that. But I'll leave it there. I need a comparison function, and in this case, the simplest one that I can write is k1 minus k2. Notice that if the two keys are equal, this works reasonably well for integers. If the two keys are equal, we get 0. If the first one is less, we get a negative value. If the first one is greater, we get a positive value. There are some reasons why perhaps you shouldn't do this, and we could do a k1.compare to k2. The reason why you might not want to do this is what happens if both of these values are very large, or if this is a negative number and this is a large positive number. And by large, I mean over a billion. You can actually overflow here, and then your comparison doesn't work quite the way that you want. Okay, fine, I'll do this. Using the built-in compare method so that it doesn't have that problem. Okay, so that builds it. Def empty on create. Actually, I probably can't test that. That's inevitably going to use the iterator. Let's just call an add get, because those are the two methods that we have. Map plus equals 5 rocket, or 5 arrow 5. So that adds that in, and assert equals that I want sum 5 when I call map.get of 5. And we should be able to run this as a JUnit test, and hopefully that green bar's good. I'd be very upset if that one didn't. Add and get, well, how many did we have previously? 7. So I'm going to build the tree that we have, 5, 6, 7, that we've been looking at. 3, 2, 4, 7, 6, 8. 3, 2, 4, 7, 6, 8. I could flip the order around here a fair bit, and I want to make sure that when I do this, copy 2, 3, 4, 5, 6, 7. And it really shouldn't matter what order I get these in. 2, 3, 4, 5, 6, 7, 8. And if I run that, and there we go. So we got a green bar. All of these tests passed, and we can feel at least reasonably confident about our if this isn't working, we're getting remarkably lucky in the ability to get things after we've added them into the tree. So that shows you our adding and our getting. In the next video, we'll come back and we'll write our iterator and test it as well.